Okay, hello everyone. I'm Larry Samuelson. It's my great pleasure to welcome you all to the 2025 World Congress, to the beautiful city of Seoul, to the COEX Conference Center. The Econometric Society is arguably the only true global association for academic economists. We think we have an important role to play in guiding the development of economics and econometrics. We do this by publishing 3 journals, but especially we do this by bringing people from throughout the world, from the 6 regions of the Econometric Society together. We do this in an ordinary year with 11 annual regional meetings, up to 9 schools and workshops. It's a great honor for me to be part of this society and to happen to be this year its president. The World Congress occurs once every 5 years. It's the focal point of the society's meetings. And so I welcome you, economists from all regions of the world, 61 countries, all career levels, all aspects of economics, reflecting the very best work in the profession. We have more than 2,500 people registered for this Congress. Makes it the largest, the most diverse one that we've had. We've got a great lineup of programming for you, in addition to Magne Mogstad, who I will introduce in a minute. Later this week, you're going to hear Zaki Gilboa give the Walras Bowley Lecture, Silvana Tenreo give the Coles Lecture, Hidi Ichimura give the Frisch Memorial Lecture. We've got 4 pairs of invited talks each morning for you that will span the range of the discipline. We've got about 1,700 contributed papers. Now, before I get to the introduction, it's my job to say thank you. I have a lot of people to say thank you to. I want to start by saying thank you to our local organizers, Jinwoo Kim and Yoonjae Wang, out here somewhere, I presume. They did a wonderful job of drawing all of this together. I'd also like to thank Young Sung Chang. He began as a co-editor, then he became a member of the board of the central bank, and so had to step down as co-editor. These organizers brought together a number of institutions that I have to thank. This is a long list, and part of the point is that this is a long list. As part of the sponsors and organizers for this Congress, we had the Korean Economic Association, Seoul National University, Korea University, Sogang University, Sungyang Kwan University, Yonsei University, the Bank of Korea, the National Research Council for Economics, Humanities, and Social Sciences, the Korea Development Institute, the Korea Institute for International Economic Policy, the Korean Econometric Society. I think it's impressive that anyone could organize that many institutions to put on this Congress. I also have to say thank you for financial support to the government of the Republic of Korea, to the Seoul Metropolitan Government, and to a long list of private and association corporate sponsors that you can see in the program. Now, this Congress wouldn't have been possible without a great deal of work by our program chairs, led by Rachel Griffith from the University of Manchester, and including Yuri Gordonachenko from Berkeley, Michi Kandori from Tokyo, and Hidi Ichimura from the University of Arizona. They're responsible for the programming you're going to see. And finally, especially, I want to say thank you to the staff of the Econometric Society. This is Rito Johori, who's our Director of Events, Lynn Hogan, who is our Executive Director, Bart Lipman, who's our Executive Vice President. These people spent collectively much of the last few years thinking about this event. all of the last few weeks, every minute of the last few days, and so I thank them for a job very well done. Now, finally, I come to Magne Mogstad. He's the Gary S. Becker Professor at the University of Chicago. You can look at his webpage and find all sorts of biographical details that I'll skip. I'll just touch on why he is, in my view, the personification of the type of work that the Econometric Society is proud to be a part of. His work is broad. It includes applied contributions. It includes contributions to econometric methodology. You can see in his work economic theory, you can see statistics, you can see data in his work. His work touches on topics of important current interest: inequality, labor markets, policy, as well as theorems. He has been the editor of the Journal of Political Economy. He's a fellow of the American Academy of Arts and Sciences, of the Econometric Society, of course, of many other societies. So I'm very proud to give you Magne Mogstad, who's going to give us the Fisher-Schultz Lecture.
Thanks, Larry. This is joint work with Ingvild, Lancelot, Alex, and Oscar, all of which used to be at the University of Chicago. Oscar just started a new job at Harvard. But, you know, Oscar is a nice guy, and you shouldn't hold that against him. So what we want to think about is empirical analysis of supply and demand in heterogeneous markets. That's going to be the topic of the paper and the talk. So we're going to think about a classic problem, demand and supply for a single homogeneous good across multiple markets. The demand for this good and supply for this good is determined by these structural equations, QD and QS, that tell us how much you demand and how much is supplied as a function of price, given Z and B. Z is going to be observable characteristics of the market. It may or may not include an instrument, in which case it will be excludable from one of the equations. And B is going to be the latent variable, the unobserved heterogeneity. We're going to be very, very flexible on that until I tell you when we're going to make a restriction, but for now it's going to be completely unrestricted. Maybe non-separable, maybe multidimensional, and the C and B determines, you know, the differences across markets. When we're going to assume that the data we see, the market is going to be in equilibrium, so the observed Q and P are given by demand equals supply, or may also be represented by the reduced form equations, QE and PE, which tell us the price and quantity as a function of C and B. Okay, that's going to be the model. And we're going to think about, given that you observe Z, P, and Q, what can you learn about the demand, the structural demand, and structural supply functions, or some function of it, say deadweight loss or consumer surplus. Okay, so you might ask, like, why are you doing this? Isn't this a solved problem? It is a solved problem in a constant effect case. I mean, it's an old classical question about demand supply for a single homogeneous good. In the case of heterogeneity, there's much less work, and we're going to argue that some of the results that's out there, they may look very negative, sort of negative results when you can get point identification. We're going to argue that you can actually learn quite a lot in interesting cases, even if you're not point identified. So for those of you who work on like IV or follow that literature, there's a lot of work on how to think about or work with unobserved heterogeneity using IV to identify treatment effects or the effect of policy or the effects of intervention. These kind of models are going to have like a choice equation or a first stage and an outcome equation. And you're going to have some shifter, and you can allow for heterogeneity treatment effects under different assumptions. We're not going to think about that setting. We're going to think about demand and supply instead. It's not the first stage and the outcome equation, but two equations that are tied together, and you're going to have a simultaneity coming up in the sense that they're simultaneously determine the price and the quantity. So this is an age-old, at least it goes back 100 years in economics. It's a nice paper by Wright, talking pretty clearly about demand supply and what you can learn. Also Schultz, whose name is on this lecture, I think, thinking less clearly, I would argue, about demand supply. And then Goldberger has a very nice Fisher-Schultz lecture thinking about structural equations in economics, and much of this is demand supply. And there's a nice discussion actually about Wright and Schultz and the different views on that. So we're going to depart from that literature in one important way, the beta. We're going to allow for this heterogeneity across markets. Why? Well, because it's actually pretty hard to write on a model, reasonable model where you don't get this heterogeneity. You need to have, as you're going to see in one application, very strong assumptions about the primitives and how they vary across markets. We need the same distribution of consumers, similar technology, similar supply functions for input, and so on and so forth. So it seems natural to let that vary across markets. So there are some results in the literature already. We're going to talk quite a bit about those as we go through. There's a nice paper, or series of papers by Chuck Mansky, thinking about or trying to derive sharp bounds on the quantity demanded at the hypothetical price. Not the price you observe, but some other price. Using, the only restriction he uses is demand is downward sloping. Okay? He derives a sharp bound, so those are the best bounds you can get given the data and assumptions. But for the things we're going to be looking at, those will not be the sharp bound. And in fact, the approach it takes is not going to get you sharp bounds. Because we're going to be interested in thinking about the demand function, so the slope of demand, or consumer surplus and producer surplus and deadweight loss. And his approach is going to turn out not to be really the way you want to attack that problem. I'm also going to talk about work by Josh Angrist, Imbens, and Grady. We're going to use their application. So they basically have a paper thinking about, suppose you have estimate a special case of that model, constant effect and linear demand supply. You use 2SLS, you have an instrument, say on the supply side, you run 2SLS, and they ask what you get if the true model of demand supply is like this. It's heterogeneous and nonlinear. And you're going to argue that you get something. Okay, we're going to argue that that something is not very interesting. And we're going to also look empirically that something is different from what you get if you try to bound the interesting things. There's also work by Rosa Matskin and Barry and Hale that is about these kind of models. The key thing that they do in that case is they assume that beta is scalar. So it's a single dimensional observables, and then you're going to get essentially like a rank invariance that allow you to identify these demand and supply functions with some additional assumptions. We're not going to spend a lot of time on that scalar and observable assumption because it's really very restrictive in terms of the underlying economic problem. And the last paper we're going to talk a little bit about is Matt Maston's paper. It's in some sense the point of departure of this project. I think it was his job market paper, where he showed what assumptions you need to point to identify linear demand supply with heterogeneous markets. So in that case, the QD and QS are going to be linear in a given market, but the beta determined heterogeneity is going to be unrestricted. And he has some pretty negative results, is my reading on the paper, where he argues that you need like a full support instrument, continuous full support instruments, which basically means you need to be able to shift prices from basically 0 to infinite, okay, through shifting the cost, whatever you have an instrument, the cost shifter or tax subsidy, something like that. Otherwise, you need to start making parametric assumptions. And in his discussion at the end of the paper, he sort of says, these are kind of like negative results, but we think you can do something if you think about partial identification, and it might be possible to learn more. So that's sort of the point of departure of this project. We want to think about what we can learn, not with this crazy continuous full support instruments that we never have, but with data that actually is available. So we're going to think about discrete instruments, often binary. We're not going to impose arbitrary assumptions about heterogeneity, at least not in the beginning, maybe a bit towards the end, to learn the most. We'll think about only using economic restrictions, such as downward sloping demand, upward sloping supply, and so on and so forth. And we're going to show non-parametric without putting any restrictions on beta, what you can learn. It's going to turn out you can learn quite a bit, at least in one application. And we're going to show the sharp bounds, so you can try out. But I think most importantly for that exercise is going to convey the intuition why you can learn something. Okay, the non-parametric case helps convey sort of the underlying intuition of the problem and why these economic restrictions may help you learn something. Once we have done that, we're going to impose some more assumptions. We're going to go to the classic linear demand, linear supply. So each market is linear, but there's arbitrary heterogeneity. So the slope may be like arbitrarily different across markets. It doesn't have to be linear. You can make it like quadratic or put some structure on it. But it's going to help a lot to have some structure on the underlying demand function. So this is the same problem as Mastin. We have this negative result. And we're going to show that those negative results, while they're correct, they're not really that binding. Okay, you can learn a lot. In other words, you can partially identify interesting parameters through linear demand and linear supply. And the key intuition for that is going to be that linear demand and linear supply gives me linear reduced form. And linear reduced form is what you're going to see in the data, the quantity, equilibrium, quantity, and price. And once you know that it's linear, it's going to put a lot of restrictions on how the data can be given a model. So we're going to turn around not to point identify stuff. We're going to learn a lot. And then we're going to think about a third way. Why do we need like a third way, given like the functional form on a given market, like linearity gives a lot? Because we're going to run into Curse dimensionality. Once you get a large number of markets, or a large number of instrument values, a large number of covariates, our approach is going to turn out to be pretty hard computationally. So we're going to think about a case where you have smooth heterogeneity across markets. I'm going to be precise what I mean by that. But think about like a mixture of say, like, normal distributions or mixture of normal or something else. So it's allowed to have a lot of heterogeneity, but it kind of have to be smooth. And that's going to solve this Curse dimensionality. And we're going to apply that to a setting where we have a large number of markets. So we're going to think about two empirical applications. First, we're going to go back to the Angrist Imbes-Grady application. It's looking at the Fulton fish market. The instrument is going to be like, the weather, going to be shifting around supply. Why do we look at that application? Well, because, it's kind of nice to compare to what they find using 2SLS, what you get with the constant effect. These are like established papers. The other advantage is there are relatively few markets, 111 markets. It's easy to show what the non-parametrically what assumptions give you with a finite number of markets. Then we're going to go to the third point there with smooth heterogeneity and ask a more substantive question. We want to figure out what is the incidence and efficiency loss of sales tax in the US. We're going to use the Nielsen scanner data and reforms of sales tax across the US to think about that in the demand supply setting and try to bound and learn about these economic parameters. For that, we're going to have thousands and thousands of markets. So we're going to need some smoothness in heterogeneity. So that's going to be it's going to be the paper, and that's the talk. Okay, so we're going to start off with these structural demand and supply functions, which implies this reduced form. We're going to assume throughout that we have unique equilibrium in each market. So for each C and beta, we know the sign, and therefore it's going to be unique. So in this particular case, that's not really like a very strong assumption. For a non-parametric part, it's going to be a bit easier to work with what we call potential outcome notation than the latent variable notation. Once we go to parameterizing heterogeneity, it's going to be easier to have the latent variables. But it doesn't matter, it's all notation. So we're going to have the capital QD and capital QS. You might say, what happened to beta? Well, beta is going to be implicit in this function. It's going to be heterogeneous, it's going to be arbitrary. Okay, give me a P and C, and then this function tells me the demand and the supply. Okay, it's just another way of writing the same thing, where the beta, the latent variable, is implicit in the potential outcomes. It's kind of what Angrist and Imbes and others have been doing when they think about Ivy. And it's going to be easier because we don't have to carry with us the beta, but we're not making any assumptions about it. Okay, so the starting point is going to be that we observe the left-hand side there. What's the left-hand side? Well, that's a share of markets with C equal to C. C is a vector of observables. So the share of markets with certain observables that have the equilibrium price and quantity below P and Q. Yeah, that's going to be the data. That's what we observe in the data. Without further assumptions, you can get the equality, which just tells me that since we assume that we're in equilibrium, then the observed price and quantity is also going to be the equilibrium price and quantity for those markets. Okay, that's without any assumption. If you assume that C is exogenous, in other words, like independent of the structural functions, so not really an instrument yet because it's not excludable, but it's randomly assigned, then you can learn a bit more. You can get the equilibrium price and quantity not only for the markets with C equal to C, but also for markets with different values of C. Okay? In other words, you can learn the causal effect of C on equilibrium outcome and prices. But that's not really what we're after. We want to learn about the structural functions, or the function of that, and that's harder. Even harder if I assume that it's excluded. One of the C's are excluded from demand or supply. And the reason that's harder is because of simultaneity. The simultaneity means that reduced forms, which you can learn from an instrument or an exogenous C, is only indirectly related to the underlying structural functions, except in a special case where you have like perfectly elastic supply or demand. In that case, you're back to the standard IV problem, get an instrument, shift around prices, you can learn about the demand function. In the general case, with simultaneity, you don't learn about the underlying structural functions by just having an exogenous C or even excludable C. So that's going to be the starting point. It's also the starting point of Mansky 94-97, where it derives the bounds on structural demand. So that is interesting in the left-hand side. It tells us the quantity demanded at a given price for markets with C equal to C. So you also know the share of those markets that are demanding less than Q when P is equal to a fixed value P. Not the observed one, but the hypothetical one. So his bound is there. So what is he doing? Well, the lower bound, the intuition is the following. Okay, he's only going to use downward sloping demand. C is not an instrument. All he says, he knows the sign of demand. Okay, which means that for the lower bound, you're going to have to include those markets that demand more than Q at a higher price, right? Because if they demand more than Q at a higher price, they also need to demand Q at a lower price. So that's going to be the lower bound. The upper bound is going to be excluding those markets that demand less than Q at a lower price. Okay, because if they assume less than Q at the lower price, they also need to demand less than Q at the higher price. That's it. That's what you get from downward sloping demand. This is going to be sharp. They're not going to be very informative. Okay, economically informative. Okay, in the applications we look at, it doesn't really have an application, but it's a nice starting point of thinking about what shape restrictions give you. So you might ask, what if I have an instrument, which we're going to have? It doesn't really have that in the first paper. So what's the instrument going to be here? I don't know, like a tax or a subsidy or some cost shifter or something. Let's imagine we have that on the supply side. Okay, the instrument is defined by two things. It's going to be exogenous, so it's going to be jointly independent of the structural equations, and it's going to be excludable. So it means that it enters one of the structural equations, in this case supply, but not demand. Okay, under those assumptions, you can do the Mansky-Pepper bounds. They don't really think about demand supply, but then the same arguments go through. That you're going to look across all these values of C. Okay, why can you look across the values of C now? Because, C is randomly assigned. So for each a market with C equal to C and C equal to C prime, those markets should have the same underlying demand. Okay, why? On average, or the same distribution of demand. Why? Because it's randomly assigned. Also, it's excludable from demand but not supply, which means price is going to vary, even though demand doesn't vary. So now you get to see the same underlying demand function at different prices. That allows you to learn about, of course, the demand function. And what you could do is to pick the smallest value for the upper bound and the largest value for the lower bound across the different values of C to get, which is the intersection bound, to get a new bound. Okay, again, these are going to be the sharp bounds on that particular counterfactual, which is the demand at a given, the quantity demanded at a given price. But neither this or the previous bound is going to tell us the sharp bounds of what we're interested in, which is going to be the slope of demand or the deadweight loss or the functionals of that. Why? Because these are point-wise sharp bounds. They're not going to be sharp for a difference. In fact, they're going to be very wide, and they're not going to give us much. So we can't use this approach, but this is an approach you could use if you care about that particular counterfactual. Okay, but those are not our question of interest. So that's sort of the motivation of our paper and talk, that although there exists a partial amplification approach to this, he looks at a different set of parameters using a different approach. So we want to do something else, and we need to do something else. Okay, so what do we propose to do? So it's useful to start out with the basic problem, what's not the problem, and what is the problem. The IV assumption gives us identification of the distribution of y of z. What's y of z? Y is just like notation for the outcomes that we see, the equilibrium outcomes, price and quantity. If you randomly assign the z, it's excludable. I learn about p and q for a given z, and for other values of z. But that's not really what we want to learn. We want to learn about how the pair of p and q are at different prices, because we want to learn about the function. We want to say the slope of demand. It's a comparison of quantity across different prices. Okay, so that's the problem. How do we get, for that we need to know something about the joint distributions, not only the marginals. That's going to be the fundamental problem that we want to tackle. We want to learn about the joint distribution of these PQ pairs across different values of C. Okay, so to fix ideas, I'm going to go through some graphs, which is going to convey an intuition of what different assumptions give you and our approach, and then I'm going to go to like the more general problem. But I think these graphs are pretty useful, at least for us, to understand what's going on, and we can explain how they generalize beyond this kind of simplest case. In those graphs, we're going to have a binary instrument, say like a substance, high-low, and then we're going to have this W, which is going to be a collection of those Y0, Y1. In other words, a collection of those price quantity points for different values of the instrument. So Y0 will be the price quantity when C is equal to 0, and Y1 will be the pricing quantity, equilibrium pricing quantity when C is equal to 1. So we're going to think about for each possible combination of those price quantity pairs, we're going to call it the market type, we're going to ask two questions. Is there a demand-supply curve compatible with those pairs? Is it downward sloping? Is it upward sloping supply? And so on and so forth. And if it is, how can we bound the target parameter for that pair? And how can we average across all the markets? Let me sort of show you the simplest possible case. We're going to go through more general cases and with different assumptions. Where's the simplest possible case? Where you have only two price quantity pairs for each value of the instrument. In other words, there are two types of markets. Okay? Two types of equilibria for any given value of Z. You have the Y0I and the Y0J. Okay? We don't know whether Y0I should be linked to Y1Ji or Y1J. We only see the marginal distributions. Okay? But I can guess, I can construct all these possible linkages between those equilibrium outcomes when C is equal to 0 and the equilibrium outcomes when C is equal to 1. And since C is randomly assigned and excludable, it should be the same underlying supply and demand functions for C equal to 1 and C equal to 0. So what are going to be those? It's going to be, in our notation, W1, W2, W3, and W4 are all the possible combinations of price and quantity across these candidate markets. For each of those, I can compute one possible target parameter, the average slope of demand, and I can see whether that satisfies basic economics. In this case, it doesn't. Y0J can't be linked to or paired with Y1J because it would imply that demand has the wrong side. I can rule out that. Once I rule out that, I'm actually point identified. Why? Because now I know that Y0J must be linked with Y1J, while Y0I it can be linked to Y1I and Y1J. How much is linked to each? We know because we know the marginal distributions. Okay, so just by downward sloping demand, the way I drew this example, you get point identification of the joint distribution of PQ pairs across these things. That's going to be true no matter what the distribution of of y given c is, but the value is going to change. So I'm redrawing the same graph, but now I'm putting some weights on these points. Suppose it's like a uniform distribution of y given c. We would see that in data. That's something I would know. Suppose we're in a case where it is uniform across those equilibria. So there are equally many y0i and y0j equilibria, and the same for y1i and y1j equilibria. In that case, I need to link all the y0i markets with y1i markets, and all the y0j markets with y1j markets. Okay, so now I can compute the average slope of demand for markets like market type y0i. It's just going to be the slope of these things, or the average across the different markets. Here's another example where it happened to be that the weights are such that you have more of the y0i markets than the y0j markets. You remain point identified. But in this case, the average demand of y0i is going to be a mixture of the slope between y0i and 1i and y0j and y1j. So even though in this case we're point identified no matter what the marginal distributions look like, then the value is going to matter. So that's going to be information we need to carry with us to compute the relevant target parameter. So you might think this is kind of a stupid example, 2 types of markets. What if it's 3? We're going to lose information then, or can we get more? So it's going to turn out that like the number of market types, it's not like this becomes harder with more markets, you're going to learn less. It depends on how the data is. Okay, here's an example where you're going to learn more with more markets than you would have done with fewer markets. Okay, so let me draw this one. Here's the data. You have the y0i, y0j, and y0k. These are the equilibrium price and quantity when c is equal to 0. And then you have the y1j, y1i, and y1k, which are the equilibrium outcome and prices when c is equal to 1. If you start with the y0k point, you can ask which one can that be paired with? Well, it can only be paired with 1 if you have downward sloping demand. So we know that one. Okay? If you assume that the marginal distributions are uniform, then we know that y1k can't be linked to y0j or y0i, the dotted lines. You can remove those two. And now we can move to y0j, which only can be linked by the same argument to y1j because of downward sloping demand and the uniform data. And then we can do the same with the y0i. So in this case, you get point identification. But if I change the marginal distributions, I may not. Okay, so that's also something you need to collect and use in the identification arguments, because all these dotted lines are going to come from essentially adding up constraint. Like once I rule out some of those dashed lines because of theory, then I need to make sure that those guesses are internally consistent, so it adds up. Also, if I remove one of those points, suppose I have a different data set without the first data point, so all the weight is on y1j and y1k, then I'm partially identified. So it's not the case that having like many markers is bad for us and few markers is good for us. It really depends on how they are structured and how they're organized. So that's the simplest case. We'll only use downward sloping demand. But we're going to start imposing other assumptions. I want to walk through the identifying power of those before we start thinking about how to do this, not with like 2 or 3 markets, but with many markets, potentially a continuous number of markets, market types. So this is another example where you have 2 types of markets, y0i and y0j. In this case, we don't learn anything from theory. Okay, you might think this is kind of surprising. How can like y0j be below y1i? Well, because we haven't assumed anything about the first stage. We haven't said anything about whether the instrument is supposed to reduce prices or increase prices. Okay, if you assume inbesanguis spontaneity, which means I know something about how the instrument is supposed to change the equilibrium outcomes. Say you have a tax subsidy or like imposing a tax on this firm. In that case, you would know the sign, probably. That's going to give you identifying power. Because it's going to mean that y1i can't be linked to y0j because we know that demand equilibrium outcome should be higher when the instrument is switched off than when it's switched on. So now we can rule out this one. Also, this assumption combined. Here's a case where you have like 3 types when the instrument is switched off and 2 types of equilibrium when it's switched on. You can rule out y0j to y1i because of downward sloping demand, and you can rule out y0k to y1i because of monotonicity, in which case we end up being point identified. So you start layering more and more assumptions, you start ruling out more and more of these things, and that's going to turn out to be pretty powerful empirically. That it's not like we just like start adding assumptions and it becomes like additive in terms of the identified power. They start interacting in interesting ways as you go along. The last assumption I want to emphasize non-parametrically before we start getting to what we do at scale is this assumption that's sort of fleshed out in a paper, very short paper, Econometrica, in 2018, 2 pages. It's a beautiful paper, I think. Takes a standard public finance argument to demand supply. They call it the Ramsey exclusion restriction. All they're basically doing is the following. They're saying that, assume that a dollar is a dollar. So how much you're going to supply at price P doesn't depend on whether that price is coming from a subsidy or a tax, or if it's coming from the willingness to pay for consumers. Okay, so it's just saying a dollar is a dollar for the firm, which means you can write the supply function as the price plus the tax or the transfer T, which is randomly assigned. In a constant effect linear demand supply model they look at, it allows you to identify both demand and supply. Why is that? Because the coefficient of the instrument in the first stage becomes the supply function. Why? Because dollar is a dollar. The effect of the instrument on the price is the supply slope, which means you can identify the supply from the first stage and the demand from the subsequent, the second stage. In our case, it's not exactly the same because it's not going to be a constant effect, which turns out to have a lot of identifying power. So I'm going to show that in this graph, because we're not going to have a linear constant effect, we're going to have a heterogeneous one. But it's going to sort of give us a lot empirically. So let me walk you through that example. Take the type of equilibrium y0i, and now just subtract off the tax. Okay? When c is equal to 1, they have to pay tax t, okay, on the quantity sold, which means they're going to supply now at the producer price p minus t. Okay, so now you get the point on the supply curve. We know that that's linked to y0i because I just subtracted off that amount. Because supply is upper sloping, it has to be linked to y1i. So only equilibrium can be linked to, so I know the supply of that. The same with y1j, which is subtract off the tax from y0j. And this has to be linked to y1j. So now we know that supply. And y1j can't be linked to y1i because we violate upper sloping supply curve. And once we know those linkages, we also can infer the demand, right? Because now we know that y0i is linked to y0i correspond to the same market just at the before tax price. So it's linked to y tilde 1i, which is linked to y1i, which then must be linked to y0i. So we get a full system here by using their, I think, pretty clever Ramsey exclusion restriction. You might ask, when would it fail? Well, if you have some sort of lack of salience, suppose consumers don't see, like in the US, you have sales tax, they don't see the after-tax sales tax price or something like that on the tab, then this may not hold. Otherwise, it's just assuming a dollar is a dollar and people know the prices. Then you get something for free by knowing the type of the instrument. Okay, which is not really how we teach, at least I teach econometrics. You can sort of count number of endogenous variables, number of instruments, but what the instrument is matters, because there's going to be some theory restrictions from that. So we're going to use that actively. So those are like the type of assumptions we're going to be working with. We're going to think about sign restrictions on demand and supply, sign restrictions on the first stage, because you know something about the type of instrument, but also you might know something about the units of the instrument. If they come in dollar values, like a cost shock, tax, or a subsidy, you can exploit that by thinking about after tax versus pre-tax prices, to trace out something about supply and demand at the same time. So we're going to use those things, and we want to now think about, given those assumptions, with no restrictions on beta, completely non-parametric, what can we learn about demand and supply, and functions of that, like consumer surplus and deadweight loss. Okay, so what's hard about that? Well, first of all, we need to figure out those pairings, which one are possible given the theory, and given the adding up constraints. That's learning about the distribution of W, the distribution of the QP pairs, the joint distribution of the QP pairs. But suppose you know that. After knowing that, or bounding that, we need to think about the target parameters. In some cases, it's not going to be, it's going to be the same exercise as learning about the W. For example, if you want to figure out the average slope of demand between the equilibrium prices, that's just like, if you know the distribution of W, or what you can learn about that, you know that too. In other cases, it's not going to be like that. Think about the consumer surplus between the two equilibrium prices. That depends on how the shape of demand is between those prices. You're going to need to bound that. You're going to need to interpolate between the prices. Same with deadweight loss and so on and so forth. So that's going to add another layer of complication into this partial identification. We first want to learn about W, and given what we can learn about W, we want to learn about the target parameters. Some cases, it's going to be trivial when they're non-composite. But in the case of composite, which means it involves equilibrium prices, but also something else, extrapolations or interpolations, it's going to be much harder, or at least harder. So we want to think about that. So that's the intuition in a non-parametric case. So now we're going to think about how to actually use that intuition to learn something from real data, not this simple like 2 types of markets or 3 types of markets argument. But I think that sort of fleshes out the intuition of why we're learning something. And how it's different from the Mansky paper that looks for a given C. It looks at things, but we're looking across the C's all the time because we want to learn about the comparison of QP pairs for different values of C. Okay, so what's going to be how are we going to do this in practice? Well, you could have done this to sit down and by hand compute the bounds by figuring out all the possible combinations and given those what the demand and supply curves could be. It's going to be very tedious. We're not going to do that, so we're going to solve this at the computer. So we need to show that we can compute the sharp bounds using our approach. Okay, so that's what we're going to show to you guys now, and we're going to apply it in a bit. We need a little bit of notation. I don't think the pointer works on this, but I was told, but let me point with my finger. You're going to have the functions Q, they're going to be demand supply functions, just a collection of that. And F is going to be distribution. It's going to be distribution of the latent variable if you want. It's going to follow some distribution, F dagger. Then you're going to have, they can be unrestricted, they can be restricted, depending on what we assume. The target parameter is going to be the expected value across F of some tau. Tau is the target parameter at the market level, say the average slope of demand or the deadweight loss, and then you average across those markets, depending on what you want to learn about. And what we really want to do is to solve this problem. We want to find a sharp identified set, at least the max and the min of the target parameter, and make sure that we satisfy assumptions, downward sloping demand, upward sloping supply, other things, which impose restrictions on the F, and then we match the data. Okay, matching the data is making sure that we get those points I showed you. Okay, so that's going to be what we're doing. We're going to think about 2 environments, as I talked about, when they have finite support. Okay, in that case, we can stay completely non-parametric and do this. And in cases where there's no restrictions on the support of Y and C, so you might have like continuous Y, continuous C, loads of markets. In that case, we're going to have to, for computational reasons, we can work with a flexible parameterization of F. It can be like a mixture of normals, or mixture of normal and beta, something like that. But we can't be completely non-parametric. We're going to start talking about 1. We're going to go to 2 in a bit. 1 is basically just the formal part of what I just showed you in figures. Okay, so what do we do and how do we show sharpness? So in this case, with like a finite number of markets, or types of markets, not markets, but types of markets, this is what we're going to be doing. The first step in the computation and the computation proof is the following. Make all the guesses of the pairings. I think we call it tuples because it might be more than like 2, but all the possible tuples of equilibrium outcomes. So that's what I did when I draw these lines. Okay? Remove those that are not consistent with the theory. Okay? Whatever assumption you impose, that's the dashed ones. Remove those, and then collect the rest. Step 1 in this computation, I'm going to show you how we do it. Step 2 is going to be for those candidate markets that's consistent with the theory. Compute the max and the min of the target parameter, say average slope of demand, the consumer surplus. And then step 3 is the dotted, not the dashed lines, but the dotted line. Make sure it adds up. Okay? So you have to make sure that your guesses of different markets are internally consistent in the sense that it needs to add up with the data, so you can't match one market with all the other possible markets. That's the third step. Find the pi's. The pi's is the weights on the omega, the joint distributions, that are consistent with the data. And then pick those and compute an average across the markets. What we show in the paper is the following, that you get a sharp identified set. It sort of builds some work that me and Alex did before with Santos. And we can show that for every f in f dagger, which depends on the assumptions you made, that match the data defines a feasible pi. And given a feasible pi, we can construct the f in f dagger that matches the data. In other words, this is going to be the sharp identified set, and it comes from sort of the structure of this problem and the linear programming structure that's there. So we know that we can have 3 possible solutions. You can be a point, in which case your point identified. It can be no solution, in which case the model is wrong. Or it can be multiple solution, in which case you're partially identified. And you have guarantees of finding that because of the linear programming structure. So that's going to be the computational approach we take to the graphs I just drawn for you. Here's how it looks like in data. This is the fish market application of Angrist and co-authors. Grady was, I think, a PhD from MIT. He has it in his thesis. It became like a nice sort of method paper in 2000. And in some sense, this is the... So Imbes and Angrist got the Nobel Prize for the late paper. This is the late paper applied to demand and supply. Okay, so the same argument. They're saying, I'll talk about it in a bit what they're saying, but they're just saying, can you get the causal interpretation of demand supply if you misspecify the model as constant and linear? We're going to talk about that in a bit. We're going to use the data here. You start with no assumptions. I mean, you get very wide bounds. You impose downward sloping demand. It helps tighten the bounds as you would expect on one side. You rule out the most inelastic part of demand. You assume that the instrument satisfies monotonicity. In his case, the instrument is stormy weather. So that seems plausible. It's a storm, supply goes down. So that helps a bit in itself. You combine the two, and you get pretty informative bounds on one side. You can rule out, you know that the demand has to be pretty elastic. What's the last column? That's the 2SLS estimate. Okay? So that's what you get from running this model, assuming constant effects, or doing the reverse engineering argument of Angrist and co-authors. So that's outside these bounds, which means that you can kind of like, these are so few observations that I don't think you want the inference of testing here, but at least the point estimate is not consistent with the data. So we learned quite a bit. We learned that the demand for fish is pretty elastic, and more elastic than what the 2SLS estimates would tell you, without making any assumptions about the functional form of demand within the market or across markets. So that's the non-parametric application we're going to have. Then we're going to go to the classic case, linear demand and supply. Okay, it doesn't have to be linear. It can be like log linear, or it can be like some sort of parametric model of demand within a market. Okay, so we want to think about that, partly because, that's the model that a lot of people use. Think about like, Katz-Murphy demand for education, labor supply, labor demand. It tends to be like some sort of log linear or linear demand model. What we're going to object to in this paper or do something about is not that per se, at least in this case. It's the homogeneity assumption across markets. I'm gonna, in our application, we're going to show you what that means in terms of the primitives of the model, but let's just walk through what we're going to do in this case. So this is a special case of the general model. We're going to start with just linear demand, and we're going to impose linear supply too, and explain why that helps a lot to have both being linear. And that's going to be the same model as Mastin had in his paper, and also the same as like Wright and others had with constant effects. So what we're going to say is that you have this demand model, QD, where beta 1 is the intercept D, and beta PD is the slope. Those are going to be like random, so they're heterogeneous across markets. They can be arbitrary, so they may be correlated, the slope with the intercept, may be correlated with the supply side, but the restriction is that for a given market, it's going to be linear in price. How can linearity help? Well, obviously, if you have like 3 values of C, linearity is going to help a ton, because you're going to have to fit each of those guesses I had through the linear, has to be like a linear shape. So imagine like when I redraw, I can show you if you want, but if you redraw the figure I had, then having 3 support points on these things rule out a lot, because now I know that like y0i and y1i and y2i has to be linked to each other, because it's the only one that can fit the linear line, and so on and so forth. So given this, it's a little bit surprising that, maybe not that you don't get point notification, but the negative result from Mastin and others that you don't get point notification is really like it's going to turn out to be a knife edge case, and you're going to learn a lot with linear demand supply, even with heterogeneity. Let's go through that argument. The other thing that linearity helps you is the computation of the target parameter given the distribution of W. Why? Because imagine like you want to compute the consumer surplus or something like that, giving your guess about those markets, knowing it's linear is going to help a lot, of course. So those are like the 2 things in linearity help you if you just assume it on the demand side. Here's how the fish market data look like. We'll see what linear demand gives you. These are just the equilibrium outcomes and quantities, each of those dots. We're going to assume that the true average demand is going to be like this. Suppose this is what we want to learn about. Okay? We don't know it because we don't know the true DGP of that data, but assume that's the case. Okay? And now we're going to think about what we do is we take a DGP, we fit it to the fish market data, so it fits exactly the fish market data with this as the average demand. Okay? And then we're going to start with just one assumption that might be like stupid, but it gives you actually quite a lot together with some non-parametric restrictions. That's saying that we don't think the equilibrium quantity demanded at some price between like on that range there, it's going to be smaller than 4 or larger than 12. Why? Because these are like 3 times as big or twice as big as what we see for any other market in the data. Of course, we don't know this because we only see for a given market the actual equilibrium quantity price. It could be that the quantity at a different price was like 3 times different from anything else we see. We're going to put some max and min on those values, just like Mans could do in other work. We're going to drop that in a bit, but that sort of put those lines at the end there, which tells us like what the worst case could be, given that assumption. And then we're going to start putting assumptions on that. Instrument monotonicity don't give you anything beyond that, on top of it. What about downward sloping demand as in Mansky? What does that mean as in Mansky? It means that we're going to assume mean independence, not full independence. That's what we do in this paper. It gives you quite a lot tighter bounds. What if we assume full independence, which seems like natural if it's randomly assigned whether it will be mean independent but not full independent. It helps, but not a ton. That's not the assumption that buys you a lot. If you combine inverse angular monotonicity with downward sloping demand, it does help. What about linearity alone with downward sloping demand, even inside? What about Ingres Montanistic with linearity? It helps quite a bit compared to just linearity. And then, what if you combine the two? Linearity with downward sloping demand and Ingres Angris. Now you start getting pretty close to the truth for these different values. And what if we combine that with the assumption on the max and the min on the market values? Now you're very close. And if you combine all of three, downward sloping demand, bounded demand between 4 and 12 and in the market, and Ingres Angris, then you get these like solid lines, which are very informative about the demand the demand at a hypothetical price across the markets. So just linear demand combined with like ruling out crazy stuff about quantity prices plus theory gives you a ton in this case. So you might say, why do we get this result in Mogstad? Well, because he's looking for point identification. Okay, so once you sort of start thinking about partial identification, at least in this data, you learn a lot. What about supply? So far, I did not make no assumption about supply. That stayed non-parametric. Making assumptions about supply is going to help us for two reasons. First of all, it's going to help us mechanically if you think about things like deadweight loss per dollar raised. This is often called like marginal excess burden. It compares the deadweight loss of a tax change compared to like the increase in tax revenue. So the deadweight loss per dollar raised. We derive this assuming no income effects, but otherwise is a relatively general formula. We need to know, depends on demand and supply, and we need to know those. So if you know something about the supply, it's going to help for that. But more generally, even if you don't care about that, you just want to care about the average demand, knowing that supply is linear is going to help a ton because it means that the reduced form is going to be linear. Okay, the reduced form being linear means that the stuff you see in the data is going to be linear. So that means that it rules out a lot of possible combinations directly. Well, because remember that the reduced form is always like the combination of the demand and supply. And if one is nonlinear, the reduced form is not going to be nonlinear. It's going to be a complicated function of the two. If both are linear, reduced form is linear, that's going to give you a ton of identifying power. And that's going to turn out to almost get the point identified in our cases. Here's an example where we ask a real difficult target parameter given the data. We don't have that much variation. And we have linear demand and supply. And we want to bound the marginal deadweight loss in this setting. We start out with linearity, downward sloping demand, and ruling out crazy values. And then you get this value, the blue line there is going to be the excess burden, or the deadweight loss per dollar raised. Okay, we're going to think about going from like, a small, so on the x-axis, that's the initial tax rate. 0 versus like 20%, okay? So now you can start bounding these things, and you start with just the baseline model with linearity, expected signs, and bounded supply. And at least for like initial taxes are like the sales tax tend to be in the US, like 5%, 4%. You can start ruling out large deadweight loss in this fish market. If you add in Montanistic and you start bounding or crazy values on demand and prices, that helps tighten further. If you also assume that you have the bounds and Ingres Angris Montanistic, you get even tighter bounds on this with linear supply. So that's going to be sort of the analysis of the fish market paper, except I want to sort of talk a little bit about the Angris Grady paper and their analysis. As I showed you before, the 2SLS estimate that they report is outside our non-parametric bounds and way outside our linear demand and supply bounds. Why is that? Well, this is essentially a result that we derived that build on to understand why the 2SLS estimates may be giving a smaller value of demand than the bounds. So we start off with this linear model of demand and supply with random coefficients. This is the same sort of model that Imbes and Angers consider when they think about what 2SLS gives you and the weighting structure. And then, given this, we can show the following. That beta 2SLS is going to be equal to the expected value of beta, the man, the one we want, plus this covariance term here. What's that? That's going to be essentially depend on the correlation between demand and supply. Okay? So we can show that this is going to be smaller than 0 unless demand and supply are very negatively correlated. Okay? If the slope of demand and slope of supply are very negatively correlated, this can turn positive. If they're independent, it's always going to be negative. Okay? So that's what you can show formally. One thing you need to notice is it's not really clear why we care about those weights. Okay? So why does that matter? Well, the late paper is kind of nice because it tells me that even if you estimate the constant effect IV model, you get a positive weighted average of the causal effects. At least you get the sign right. If everyone has a positive effect, you're going to get a positive effect. You may get the wrong magnitude if you want to get average treatment effect, but you don't get the sign right. But I don't need that for demand supply. I know the sign. So it's not really any use to say I report something as a positive weighted average. I know demand is downward sloping. What I care about is the value of demand. Okay, which value? Well, if you only compute consumer surplus, then you're not going to care about the statistically weighted average or the economically weighted average. So I think the late paper was very nice. Doesn't really, those arguments don't really carry much over to the demand supply and the simultaneous equation. I think where we really care about the magnitude, that's all we care about. So now you might ask, or we ask at least, why do we get this different magnitude? How different are the weights? So we take this fitted DGP to the fish market data. We need to have know the true DGP to compute our weights. And we computed this. What are these? This is the weight on the 2SLS. That we don't need the DGP to compute. That's like the orange thing that becomes like, when you mix the two, you get the color that's, I don't know what it is, some dark blue or something like that. So these are linear IV weights. The linear IV to 2SLS can be weighted average of the slope of demand across markets with these weights. What about the population average? Well, that's the blue one. You take the if you take the population average compared to the linear IV, then you get the differences when you assume linear demand supply. So one is going to be basically like close inelastic, while the other one is going to be pretty elastic. Why? Well, it's because we know we're going to get this result. As long as demand is very strongly correlated with supply, negatively correlated inside the market, you're always going to overweight the least elastic markets. So you run 2SLS and you assume constant effect. If the true model is not constant, you're going to overweight the most elastic markets. So we think that's interesting because you may see that a lot. I'm thinking about Phillips curves, like demand for labor. Like sometimes we get estimates we think might be surprising, given what we think about we know about demand or supply, and we might be getting like too much weight on the most inelastic ones. Why is that? Well, you can kind of work out that pretty easily in our setup. Here's an example where you have, Y1J and Y1I are the two equilibrium outcomes or type of markets when C is equal to 1. And suppose for simplicity that Y0I and Y0J are the same in the other case. Okay, so in this case, what's going to happen when I shift supply? Well, I'm going to shift supply. In this case, I'm going to shift the price more in the inelastic market. Right, it's just what happens. And the more I shift prices, the more weight it's going to get into 2SLS. So mechanically, what's going to happen in 2SLS, you weight the markets more, the more the treatment is changing. And in this case, the treatment is the price. So you're going to now shift more the markets that are inelastic demand. And the same is going to be the case for supply. If supply is inelastic, you're going to weight those more too. And you need a covariance between demand and supply to be very negative to overturn this weighting the inelastic markets too much argument. So that's all I want to say about linear demand and supply. And say we can bound it. And those bounds tend to be very informative in this application and other applications we looked at. Partly because linear demand and supply implies linear reduced form, which is a lot of structure on the data. And at that point, there's no reason to start assuming using 2SLS and report something that's misspecified and reinterpret it as other people have done. And now I want to talk about the case with smooth heterogeneity, the third case, which is what we're going to use to estimate instant efficiency loss of sales tax. And to be honest, this is what I would use if I were to look at a real application, because once you get up to scale, a lot of the stuff we've done here is going to be pretty complicated. Maybe not for analysts or the really smart people, but for people like me, I would need to sort of speed up the computation a little bit, and the smooth is going to help us a lot. You're going to run into the Recursion dimensionality pretty quickly. It's going to be tricky. And all you're going to have to assume here is assume is some smoothness. I'll talk about what I mean by that. Yes, the basic problem is that the Fulton fish market has 111 observations, a binary instrument. That's great for playing around. Who cares about the Fulton fish market? We want to think about the real question, the instance and the loss of sales tax in the US. And in that case, we're going to have thousands of markets, and the dimensional data is going to be too high. I'm going to show you that in application a bit, but that's the motivation. For now, we want to stick with linearity. You don't really need that, but think about it sequentially. We first do linearity, and then within the market, now we're going to start restricting distribution of beta across markets. So what's going to be the restriction? Again, this is something we borrow from a paper we have in Econometrica with Santos and Alex. We think about how to bound average treatment effects through bounding marginal treatment effects. And we're going to make the similar argument here. The F dagger is a set of distributions we're going to allow for. And we're going to say that those are constrained to be in a set of distributions that are mixtures of known basis functions. Okay, what is that? Well, you can think about it as a mixtures of normals and beta distributions. And the more flexible you get, you approach something non-parametric, like a sieve argument. But you can never, without at least if you want to gain on the computation, you can never be completely unrestricted. So that's what we're going to be doing. We're going to say that the set of distributions we're going to consider have to be a mixture of known distributions. And in empirical analysis, we're going to be a very flexible mixture of gamma distributions and normal distributions. There are going to be two parameters here, the alpha and the phi. I think it's phi. The phi is going to be the weight function on the different basis functions. The alpha, I'm going to explain alpha in a bit. The alpha really comes in if you want to allow for constant effects, but on some parameters. Suppose you have some covariates, you don't want to have a random coefficient on everything, and you want a constant effect, then that's going to be essentially alpha. If you don't have any constant effects on anything, then the alpha goes away. Okay, so now we have this. So what are we going to do? We're going to solve what's called a profile in the program. It's going to have an inner problem and an outer problem. The inner problem is going to be fix your alpha, guess your alpha. Okay, just pick a value alpha. And then find the phi that gives you the best possible match of the data. What's the data? It's going to be the potential outcome, potential prices and quantity that you get from the variation in C. The best possible fit of the data, given the restrictions on demand and supply and other theory restrictions you want to make. So that's the inner problem. We're not going to use all Y and C necessarily. Suppose Y is continuous and C is continuous. In that case, it's going to be computationally feasible to do this. So then in that case, you would bin this up or use a subset of those moments. What we show in the paper is that we can derive a consistent estimator for the sharp identified set, even when you have some continuous variables. In any case, that's sort of minor, I think. That's the inner problem. What's the outer problem? That's the alpha. What's the alpha here? Well, that is a less structured problem. So you might be kind of worried. Here we're going to have a grid search. The nice thing which can prove is that dimensional alpha is always going to be low. Okay? I'm going to show you the intuition for why that's the case, but that's key to getting some results here. The dimensional alpha is always going to be low. Alpha represents essentially the constant coefficient restrictions we're going to have. And even if you have many constant coefficients, the dimension of alpha cannot be larger than 2. So you have a 2-dimensional grid search. It's going to be 1 if you have an instrument, and 0 if you have like more than 2-dimensional instrument. Okay? So why is that? Well, it has to do with the fact that we're using a linear demand supply. Okay, with linear demand supply, the reduced form is linear. The constant coefficients on covariance is going to show up as like intercepts. So for each market, if it's really constant coefficient, you're going to have like just the same intercepts shifting stuff around with different demand supply. So you're essentially going to pin down the alpha from the reduced form. So which means that, you know, this is sort of a simple computational problem at this point. It's an outer linear program, and you need to profile that out in a grid search, but the grid search is super low dimensional. It's typically dimension 1, when you have an instrument, at least, and most 2. So that's going to be the argument. Given that, we know how to compute the sharp bounds. Okay, so let me apply that and then wrap up. We can have some questions. It's always hard when you give lectures like this to know whether people are. I mean, the face that is I'm bored and I don't get what you're saying is very similar to me. So like I remember like when I was teaching like 300 students at UCL, undergraduates, who only want to get a good grade. And I have a strong accent too. I had stronger back then. And I could never know whether they had no idea what I was saying or whether they thought it was very boring. You guys are the same, so in any case, we might have questions afterwards. Maybe it's going to be the same then too, 0 questions. So I might have been extremely clear, or it's very boring again. There's not a lot of information in that. But anyway, let me go through like the application, which I think is more like the usual like the metrics application, I hope, which is like somewhere free want an application and going to have some bullshit application, like the fish market. We think this is interesting in itself. It's something that is actually why we started this project, because we want to analyze this. And then we started thinking about partial application of this and what theory might give us. Because we thought constant effect is going to be insane in this setting. I'm going to show you why. So sales tax is pretty big in the US, not as big as value-added tax in Europe. The revenue is like 500 billion. And we want to think about the incidence and efficiency loss from sales tax. What's kind of interesting in this setting is that the sales tax vary across states. So like even if you can estimate like the average demand, to think about the optimal sales tax, you really need to know how the demand is for each market. Because the deadweight loss is going to depend on the initial taxes, and you might want to have differential taxes in different places. So like it's kind of an interesting economic problem where you don't have the same federal sales tax rate. In any case, that's something we look at in the paper, thinking about sort of differential sales tax versus like the same level. So we want to think about 2 things, the instance and the efficiency loss from sales tax. You might think the instance I know are just like, you have a tax reform, you regress the effect on prices, that's the instance. Consumer prices and producer prices. Well, first of all, that's only true if you look at marginal change, otherwise you need to know the consumer surplus and the producer surplus. Second, as you kind of pointed to before, you're going to get the wrong weights, okay? You want the sales weighted to get like the real instance, not the statistically weighted, which is what the regression is going to give you. So even asking about the instance for marginal change requires a partial application approach in this setting, unless you truly believe it's constant effects. So those are the parameters we're interested in, the instance of firms and workers, and the marginal excess burden, which is deadweight loss of revenue. Not only the marginal, we're going to also look at large tax reforms. Okay, so we're not only going to look at marginal changes. So now we're going to use a linear demand and supply model, but it's going to be random coefficients, it's going to be heterogeneous. You might say, how do you get that? We thought about that at least. How do you get to be linear with random coefficients? Well, one way to do it is to use Cobb-Douglas technology at the market level, isoelastic input supply curves, and then a constant coefficient restriction means that that technology, the output elasticity and return to scale, and the input supply functions are exactly the same across all markets. Okay, so even if you think that's strong, making them the same seems kind of insane. And the same on the consumer side. We essentially need the consumers to have the same sort of underlying distribution of preferences and indirect utilities for the goods across all markets. So even if you make like functional form to make it linear and nice, the homogeneity is sort of a separate thing that you're going to have to argue, and that's what we're going to relax in this analysis. What's the data? Well, the data is going to be some mixture of Nielsen retail, Nielsen IQ. We have to approve. Nielsen makes us approve this before I can present it, and a key comment we got is called Nielsen IQ, not Nielsen. So I think they merged with some other firm, which is the IQ firm. And maybe they had IQ before, but they didn't have it in the name. So that's what we're going to be using. And we're going to see weekly sales and prices for millions of products across a large number of stores. So there's something to be concerned about there, because they may not be exactly representative. So we do a lot in the paper about trying to like reweight stuff so it matches the aggregate data and so on and so forth. I don't want to bore you with that. But it's kind of important because these are not like random samples of goods and firms. So we're going to aggregate a bit. We're going to aggregate products up to modules. It's still pretty like finely measured. And we're going to look at 6 months frequencies. There we calculate the price and quantity indices for that. And we're going to restrict the modules where we have sort of continuous data on this. This gives us like 260 goods or modules across over 2,000 counties. So that's the number of markets. At that point, we can't be non-parametric, even if we wanted, because there's no way we can solve this computational problem. So the other data we do is that we hand-collected information about the taxability status of each module. I did not do it, but some of my co-authors were doing that, and it was great because what you see in the available data or you can buy is a sales tax rate per good, which doesn't differ across goods in general in the US. But whether or not it's subject to that tax varies, and it varies at the fine level, the county level sometimes. So we need to know the taxability status of the good. These things change, both the taxability status and the tax rate, which is what we're going to be using. That's going to be our reform to construct the instruments. So that's going to be the data. Let me show you how the data, how it looks like. I'm going to run this, I think they call it distributed lag model. Basically what you're doing is that you're running a different diff with lags and leads to see how delta X, which in our case is quantity, price, and producer price, changes before and after the tax rate on the good is changed. Okay? And then you put in some controls for these are the differences. So you take out like fixed effects and things like that. We also allow potential for different trends by region and module over time. And this is how the data looks like. The different trends don't really matter much. This is what other people have used. So the prices, it looks beautiful. Okay? It's like, 0 is the time of the tax change. And there seems to be no pre-trend. It jumps up. You almost see like full pass-through to consumer prices this will be the elasticity of consumer prices with respect to tax. Okay? So again, this is an average across like, many markets. If it's constant effect, this would be great. We know it. With heterogeneous effects, just a way to summarize the data. We know this doesn't give us the parameter interest. What about quantity? Doesn't look as good, but this doesn't seem to be much of a pre-trend. It falls down a bit more gradually, which is what people typically find. It takes a bit more time for quantity to adjust to these things. So what we're going to do is to look 2 years before and after, because that seems to be like when things have stabilized, and take the long differences there. That's going to be how we construct the data for the partial identification. Take the long difference in prices, take the long differences in quantity for the treatment control, which is kind of continuous here, but like those that have different values of C. If you just run a constant effect model, you could do that by just running this long difference model that I showed you. With constant effects, you don't need to do anything else. This is the regression version of that. You get effect on consumer prices of 0.93. In other words, it's almost a full pass-through. You get the effect of quantity of 0.5. These are going to be elasticity of quantity and price with respect to the tax rate. And the producer price is 0.01. So given this, you can compute demand and supply in the constant effect model. Just take divide the delta quantity on the delta consumer price, or actually the opposite, the delta consumer price on this, and the producer price, and you're gonna get these estimates. That in a constant coefficient model, linear constant coefficient model, which is typically what people use to analyze these sales tax reforms, like Poturb and other people, then you get an estimate of 0.5 on demand. On supply, it becomes very high. Why? Because you had the 0.5 quantity divided by 0.01, the producer price change. The instance becomes small, as you would expect on the firms, given how elastic supply is compared to demand. And the marginal excess burden also becomes small, reflecting partly the inelastic demand and partly the low initial tax rates. On average, it's 7% before these tax reforms. So if you're willing to assume constant effects, you're good to go. Remember, you might ask, how do you get demand and supply? Well, I can explain you that, or at least briefly. That's a Sutton paper. If your reform is something you know the unit of, or the instrument is something you know the unit form, like a tax change, you're going to get the supply from the first stage, you're going to get demand from the second stage. So in the constant effect case, you're good to go. You learn about demand, supply, instance, and everything. What we want to know is how robust is that conclusion to the kind of insane assumption about constant effect? Is that a reasonable approximation? Or is it just giving you a very different answer? And if so, what is the answer if you allow for random coefficients and flexible heterogeneity across markets? Okay, we're going to do exactly what I did earlier, drawing those graphs. We just have thousands of markets. The data is going to be delta Q. We're going to look in differences, not in cross-section. Delta P and delta C. The main problem by differencing is that we don't get the intercept so easily. Remember, there can be covariance between the intercept and the slope, which is going to matter if you think about the optimal tax at the local level, because the correlation will matter. We difference that out, and we're going to have to need more assumptions to get it. But otherwise, differencing works fine in this setting. We can identify this, or compute this, which is the data. This is exactly what I showed you before that we started out with. The share of markets that have a change in price lower than P and a change in quantity lower than Q when they have this particular change in the tax rate. And we can do that across all tax rates, and we're going to assume that's conditionally randomly assigned. What's the basis function? That's going to be a mixture of gamma normal distributions, a very flexible one. That's going to turn out not to matter that much. We can be very flexible in that dimension, which is not so surprising given the amount of data we have, loads and loads of variation in the instrument. And here's how it looks like. These are the bounds on the population average demand across the markets. It's 0.5 to 0.68. So again, we find that to a less than to underweight or overweight the more inelastic markets. Same is true for supply. As a result, the instance is a bit higher on the firms, and the deadweight loss may be somewhat higher, but not a lot. But broadly speaking, we think this is kind of a nice result. It shows that the key conclusions of this reform evaluation sort of hold up to a major relaxation of the model, making the technology constant, the preferences constant, and the input supply functions constant. You get broadly similar conclusions. And when they differ in an intuitive way, that has to do with the fact that the constant effect model, if specified, is going to overweight the least elastic markets when it comes to demand and supply. And the takeaway is, even if you allow for heterogeneity, then nearly all the instances of consumers, which may be relevant thinking also about other changes like tariffs, on average supply is more elastic than demand, low marginal excess burden. Part of that is because the tax rate is initially low, but not only. It's also because demand is inelastic in this case. And we do an analysis in the paper, like what would have been the case if we start out with a higher baseline tax rate, which means that there's low fiscal externalities, that if you want to get more money to the government, then this might be a good way to do it instead of imposing highly distortionate taxes on labor supply and capital. So you might ask, what about large changes? Well, that's an advantage of this setup, is that we can also don't have to rely on an envelope condition or anything like that when we do the analysis. So we can look at large changes. The result seems to be very robust. So robust that Alex told me not to show this because he thinks there might be something wrong, but I don't think it is. I think it has to do with the fact that we find almost like a complete pass-through on consumer prices. And we do that almost like market by market, which means the demand has to be pretty inelastic compared to supply. So I'm going to show it, and maybe it's going to change. I don't think so. But here we go from a marginal change, which started at 0.073. That's the initial tax rate, the average one. And we change it marginally, and you get the instance of 6% on consumers. And then you start increasing it to like 0.17. And we can still sort of conclude that consumers is not going to bear any of the, or not a lot of that cost. When it comes to deadweight loss, the large reform is going to have a larger deadweight loss, as you would expect. It sort of squares in the tax rate and the change. But it's not a lot compared to like other estimates of the distortions so 0.70 means that or 0.06 means is that for each the excess margin excess burden. So for like each dollar raised, you're kind of wasting like 6 cents or 7 cents. So let me wrap up so we have time. We tried to offer like I think a new framework that's fairly general for empirical analysis of demand and supply, which is key in economics. We focus on homogeneous goods. We think about extending it to differentiated goods, which is going to be more tricky. The framework embraces partial identification. So you can gradually impose more and more assumptions to get tighter and tighter bounds. And we want to allow the researchers to go from complete non-parametric analysis to smooth heterogeneity if they need that. And this computational approach is sort of easy to apply. You don't have to read the right bounds all the time. We have 2 applications that show that you can get relevant conclusions, even under what we think are relatively weak assumptions, without having these kind of crazy super instruments that are continuous and so on and so forth. Thanks.
Thank you. Okay, we can squeeze in a question, or maybe 2 if we have one from out here. Carl.
Well, I like the restriction on economics on this year on the slope up and down. I was wondering about the linearity. I didn't see that so much. I would think you may have some restriction on elasticity, on changes in the slope, but why linearity? More parametric.
Okay, so the question for those that didn't hear it is, Carl wonders about the linearity assumption, which is perhaps a bit extreme. He wonders whether might we instead put restrictions on elasticities or on slopes or something else. Please.
Yeah, I think that's a fair point. I think we did that only that to begin with because we want to think about the linear demand supply, the classic case, the one people use, and relaxed homogeneity assumption. And then we thought, when we do that, let's think about the non-parametric case too. So it's a bit driven by how the paper evolved. But obviously, it's a strong assumption. And there's nothing about you have to have linear. I mean, you get a lot by having some sort of functional form within market. So some restriction there that ties together these data points. But I'm not going to defend linearity. But and it's also the starting point on the Mastin paper that is negative results that you can't get point identification. We thought it was like a nice way to show that's true. There's nothing wrong with this paper, but you can still learn a lot.
Okay, with the audience's indulgence, I would like to ask one. I'm intrigued by the observation early on that observing more markets may not improve your bounds. It seems at first to conflict with the idea that more information is better. We see it's not, because you see more markets, but you also generate more connections
Exactly.
that you don't know about. As the number of markets gets very large, the number of possible connections grows exponentially. Is it possible that as you observe many, many markets, your bounds get ever looser and looser? And so,
Actually not, because you're going to have a weight on those, right? So it's going to be, basically like you have a density of markets within each type. And there's going to be some restrictions on the share of the markets you can link with those things. So I don't think it's really about the number of markets per se, or that's not really like, it can be make it worse or better. And in fact, like in the sales tax stuff, where we have a ton of markets, we get a lot of identifying power. So I don't think we can kind of make it simple. It's going to be case by case, depending on the distribution of data.
Okay, we could talk about this for a long time, but unfortunately we have to go. It's been a great first day. We have a welcome reception awaiting us, so come to that and be welcome. And in the meantime, let us once more thank Magne.